It is.
It is. To put it on.
Yes. Which
There
is
must be light when you. No. Check it. And what of it works. There you go. Hola. Okay, so I think we're gonna start. Good morning to everybody. So today we have another colloquium, and on this occasion we have Professor Mavromatos from the National Technical University of Athens and the King's College of London. He is a renowned international expert on different subjects, in particular particle physics, string theory, and cosmology. And let me just summarize a little bit some aspects of his curriculum. He started at the University of Oxford. He did a PhD thesis on aspects of the low energy limit of string theories, which was supervised by Christopher Lewin-Smith and M. Daniel. And then he was a junior research fellow at Hertford College in Oxford, and subsequently we moved to the theory division as a theory division research associate at CERN, and then he got the junior faculty position in Oxford again, and finally he got the full professorship at the King's College of London, which now he shares with the university, the Technical University of Athens. Okay, Professor Mavromatos is, as I said, a renowned scientist with more than 300 specialized papers in the matters that I have described, and he has, for example, participated in, for example, a famous paper in 1998. The paper was Tests of Quantum Gravity from Observations of Gamma Ray Birds with Other People, which is a paper with more than 1,700 citations. It is a very well-known and important paper. He has also, he is having a collaboration also with experimental groups, for example, the MAGIC collaboration, the C-player collaboration, and recently in the MEDAL collaboration, which is an experiment going on at CERN, at the same place of the LHCb, in which people in this university is working. And this is an experiment in where one tries to find exotic particles, multiple charged Higgs, magnetic monopoles, and so on and so forth. So the spectrum of knowledge and capabilities, scientific capabilities of Professor Mavromatos are very wide. Let me also mention as awards and honors that in 2 occasions he shared the first prize on the essay competitions of the Gravity Research Foundation. And then he was appointed fellow of the Institute of Physics, and subsequently in 2023, so this is very recent, he was awarded the John William Strutt Lord Rayleigh Medal and Prize of the Institute of Physics, which is a very renowned prize. Let me just read for which reason he was awarded. It was for fundamental contributions to the theoretical physics especially the suggestion of quantum gravity-induced modifications of the vacuum optical properties, a proposition that led to a new arena of theoretical and experimental investigation. Okay, there is a long list, but of course I will not go into more details, but at least I should say, and I think it is important for the university, that Professor Mavromatos has visited us on several occasions, okay? He has given seminars in our group, and in particular, he has been the president of the PhD thesis committee on two occasions, on 2020 and 2023. So Professor Mavromatos obviously is very close to us, apart from being a very renowned, very well-known, renowned expert. Okay, so we are very happy and very honored to have you here. So, now is your turn. He will be talking on this very motivating and excited subject. Do we exist because of a gravitational anomaly? Let us see whether it is so. Thank you very much.
Thank you, really. Thank you. Thank you very much, first of all, for the invitation. It's a great honor for me to be here on this occasion, and on also thank you for your kind words that you said, too kind probably, when you introduced me. So why I chose this subject is because I think it's, I mean, as I was explaining, your colloquium is on cosmology, astrophysics, nuclear and particle physics. So I think this choice of talk probably is related to all of this. And well, nuclear, of course, we exist because of nuclear physics, right? I mean, clearly that you don't need to to worry about. But why cosmology, and in particular astrophysics, and some recent tensions in astrophysics may hold the key to our existence? This is what I will try to conjecture. So first of all, let me make a disclaimer here. If you Google gravity anomalies, then the first thing that comes up is this. Exactly this, United States, no other part of the planet. And it says, it defines it as the difference of the measured, between the measured at a local region of Earth, between the measured value of the gravitational acceleration and the theoretically predicted values. Of course, that is not what we are going to talk about, because that's classical Newtonian gravity. Mind you, this discrepancy between theoretical and experimental values is, of course, at the essence of all the tensions and crises that you have in cosmology, and it involves gravity, but that's not what I'm going to talk about. However, I'm going to talk about this, and I will explain what this means. This, in some sense, these are strings, by the way, and I will place them in this context and in a context which here, I'm sure you have heard several seminars on some cosmology, which is called running vacuum, some framework of cosmological framework, which was developed by Joan. And in this context, and I will explain what this thing. If I have time, and I think I will have some time, there is an amusing phenomenon recently, which they claim that gravitational anomalies might have something to do with some heat transport in vial semimetal niobium phosphide. I know these things that the speaker has just flipped, but it's not. They publish it in Nature, all right? So I will explain. It's a real gravitational anomaly. They claim that it might be related to heat transport. I am, at the moment, I'm not saying that I'm 100% convinced, but I find it quite intriguing. So I put a question mark here. But still, it's interesting. So it's interesting to see that in a diverse, if you like, set of circumstances, gravitational anomalies may have a common origin. But of course, gravitational anomalies are associated with quantum physics and not classical Newtonian gravity that I discussed before. So let me outline what I'm going to start. My motivation is the standard cosmology. I start from cosmology, from that part of your seminars. There are open issues. I include the matter-antimatter asymmetry as an unsolved puzzle of cosmology and not of particle physics that usually the particle physicists claim that they have resolved it with. We will discuss with what. Then I will move into the proposed paradigm shift. I will discuss the potential role of anomalies in the early universe. I will argue that primordial gravitational waves are related to condensates of gravitational anomalies. I will explain what this means. I will do some estimates within weak quantum gravity. We don't know what the full quantum gravity is. And then the theoretical framework that I will discuss is a string-inspired running vacuum model, which essentially is the Chern-Simons effective field theory of gravity. I will try to see why this framework can also is related to the tension, and that's the link of the tension to the existence of life, as you will see. In particular, I will try to explain why gravitational anomalies can say something about matter-antimatter asymmetry, because that's the origin of life. And at the end, I will discuss, if I have time, this condensed matter analog. So, needless, in this audience, you must have heard countless time of whatever it is. That's the status. When I was a student, the seat of space-time was considered as an academic exercise, but unfortunately, I'm probably getting old. So now the seat of space-time, omega matter, is only 0.3%, and the dark energy is 70%. We have seen so far, in the last 25 years or more of discoveries in cosmology and astronomy, we have seen all the ingredients of Einstein's theory of relativity, including we heard actually, because of the chirping properties, we have the existence of gravitational waves and black holes from merging black holes. This is the energy budget. 90%, we only understand 5%, and we believe that the lambda CDM provides a good fit for large scales. But for small scales, there is a problem. And that's where the new physics probably will come in. Why? Because the lambda CDM is in tension with measurements of the present era Hubble parameter and the growth of galactic growth data, the sigma 8 or H0. Let me start first from the H0. That's the evolution of the H0. Up to 2012, there was no problem in measuring the Hubble parameter using either CMB, which is at the redshift about 1 or higher, or much higher, or the redshift below 1, which are the nearby Cepheids, which is 0.3 and less. From 2012, they started having a discrepancy between the local measurements using Cepheids and the CMB. And you see, there is an emerging problem, because now the tension is 5.3 sigma. You see, it seems that from 2019 it was 4 sigma, now it's 5.3 sigma. Of course, that's an open area in astrophysics. There still could be statistical things we don't understand. There could be the nuclear physics of the standard, of the non-standard counters that we use for the measurement, so all sorts of things. But there could be also, it persists so far and so much that this prompted people thinking that it probably indicates new physics, fundamental physics. There is also the sigma 8 tension. They don't need necessarily to be related, but the sigma 8 essentially is the matter fluctuations within spheres of 8 h minus 1. This is the reduced Hubble constant megaparsec. And if h is around 0.67, including the discrepancy, then this tension is the same as actually some better measurements, which I'm going to use in my measurements at the end, the sigma 12. But that's the tension as well between the lambda CDM and the fundamental physics. So, but still there are many things we don't understand. We don't know the dark energy, the nature, the microscopic nature, neither the dark matter, and we haven't seen primordial gravitational waves. We thought we've seen them by detecting B-mode polarization, but it turned out to be an incorrect attribution to dust, actually, unfortunately. So to this, I will add this issue of matter-antimatter asymmetry in the universe, which usually is attributed to particle physics, but I claim that it may be attributed through a paradigm shift to cosmology. And of course, inflation. What is inflation? Is it due to fundamental inflaton or dynamical, like Starobinsky type? I will argue it's dynamical, but through running vacuum, which is not to do Starobinsky. It's due to nonlinearities of gravity, but not of Starobinsky type. So these two, the microscopic understanding of matter-antimatter asymmetries will be linked to the tensions through the model and possible alleviation, and I will focus here. Let me start from matter-antimatter, that you know, either from CMB through the standard multiple versus this coefficient of the CMB measurements, or through the heavy elements in the universe, lithium, the abundance of the heavy elements, the Big Bang nucleosynthesis, you find more or less the same value for baryon asymmetry. And the anti-baryon is very small, it's 1 in 10 to the 9. So there is a huge asymmetry of this order, 10 to the minus 10, for temperatures for the GeV and higher, which of course you explain to them by the Sakharov's condition, which assume baryon number violation, charge violation, charge conjugate violation, and CP violation. P is special reflection. And of course, departure from thermodynamic equilibrium. This is Sakharov's suggestion. And as you see, your famous painter, Dali, and Picasso. Picasso spent time in Barcelona. Dali is Catalan, was born in Figueres, as you know very well. They have predicted this CP violation because the swan is reflected as an elephant, so the elephantness of swanness is the quantum number of charge. The mirror is the water, and there is a slight color, and of course the famous Picasso paper, Girl in a Mirror. Also, you see the colors are changing, and that's the charge, and that's the parity, so this is CP violation. Well, it is. After all, that's what it is in every sense. Of course, in the real sense of particle physics, CP violation means that you have some particle which decays to leptons of the standard model and other particles, and under CP, C is charge conjugation, as I said, and P is spatial reflection. Then this is replaced by its antiparticle, and the rate of decay is not the same. And of course, you need out of equilibrium asymmetry because you may wash it out if these two processes were backwards or forwards equivalent. And however, you may also have directly generated, you can have two ways of generating matter-antimatter. First, out of equilibrium lepton asymmetry, which is called leptogenesis, from the Greek word genesis, which means birth, and leptons, and directly generated baryogenesis, directly baryon asymmetry. Of course, the standard model satisfies this condition through anomalies. That's the important point in my talk. But it's less than 10 orders of magnitude smaller, so you cannot generate the matter-antimatter asymmetry. First of all, what are anomalies? Anomalies are situations in which classical symmetry in classical physics breaks down at quantum level. Why breaks down? Because essentially, the current is not conserved, and is not only an artifact of some bad regularization. In any regularization, you will not find the conservation of this current, and therefore it's a physical thing. Equivalently, you can understand it formally for those who are experts in this in path integral measure. In path integrals, the measure of the path integral was not invariant as under symmetry transformation, and that was pointed out by Fujikawa. In 1 plus d over half dimensions through this gentleman, you can find several loops in 3 dimensions, for instance, the triangle. In other dimensions, you have 1 plus d over half external loops, and that's an exact result, and this could be photons or gravitons. And these are the anomalies. These are anomalous graphs. In 4 dimensions, this is linearly divergent with the cutoff. And it breaks the so-called mixed anomaly. If you have it in a gauge, if these are photons, you get this field term. This is the field strength of the gauge, and it's dual, which is defined like this. For instance, if this is the electric field, this could be the magnetic, and vice versa. And then there is the analog, if it is placed in a curved space-time, of the gravitational anomaly. So chiral anomaly can be induced both either by a product of electric or magnetic field, as we shall see later on, or just by gravity itself, with the corresponding dual of the Riemann tensor, which defines curvature. This is, it's not going to be very formal, the talk, but it's important to understand that because this is a total derivative, this has to be a total derivative, and you can prove that this is a total derivative. This is the spin connection, and this is the gravity connection in terms of these two terms. Now, what they break, this breaks chiral symmetry, the gauge field, which is a fermion, the exponential of gamma 5. This is the chirality matrix, and this is the axial field. That defines the left or right-handedness, if you like, of the fermion. And if present, this may break the ferromorphism symmetry at quantum level. So you may think that this is a bad thing to have, but actually I will argue that this is not. But it breaks the conservation of part of a current of the stress tension, not the whole of it. So if another important point of anomalies is that they can always couple to pseudoscalar fields. I will discuss such a coupling soon. And these pseudoscalar fields are axion-like couples. They first been discovered in the context of QCD. They've been not discovered. We haven't seen them yet. They've been suggested in the context of QCD. And the actions satisfy a shift symmetry because these are total derivatives, as I discussed before. And therefore, if you shift the field with a constant, that's a total derivative. So that's a symmetry. The axiom-like particles are pseudoscalar necessarily because you don't want to break the CP of the Lagrangian. And this means that they change sign under the spatial reflection. Now, if you have non-perturbative configurations of this gauge field, you can generate instantaneous. For instance, you can generate, because this term for these large gauge transformations is an integer, there is in the path integral, there is a symmetry. Okay, if that's an integer, the path integral is the exponential of the axion. So if you have 2 pi times an integer, that's an exponential gives 1. So essentially, you get this symmetry of the potential, and that's how you generate a mass for this. That I say for future views. Now, chiral anomaly, axion electrodynamics, the dual is the magnetic field. You have an axion couples to the product of the electric and magnetic fields via this coupling. Any pseudoscalar can lead to this. That's a triangular anomaly. And you use this coupling if you generate, for instance, a mass for the axion through this mechanism, through non-abelian, QCD as U2, you can try to find the axion through its mass and through its photon coupling through this inverse Primakov phenomenon where you have an axion. In the presence of a magnetic field, in the fluctuations of the magnetic field, you have a virtual photon and another photon, and that you get these 2 photons in B. And you try to measure the photon axion conversion. At the moment, you haven't, but these are the limits. Now, I said that these are the chiral anomalies and the non-abelian anomalies are important for the standard model. The standard model itself satisfies Sakharov condition, but not in the right order of magnitude. That's the problem. But it satisfies. And the baryon number is not conserved, although classically it is conserved, as I showed, with 3 B and 3 lepton numbers are conserved. Lepton number is a number that characterizes the kind of leptons that you have. We have 3 leptons in the standard model of the electron family, of the muon family, and of the tau family. And you see the lepton and baryon numbers are not conserved by the number of flavors that you have here, plus the U1 part, the chiral anomaly. The allowed processes are these. So this means that if you have the violation, only the lepton minus B3 number would be conserved, 3 quantities. But if we have already observed the neutrino flavor oscillation, so the L minus B is conserved, 1 quantity, and the total lepton number only, because an individual lepton number is violated because you have oscillations between flavors. An electron neutrino becomes a muon neutrino and vice versa, and a tau neutrino and vice versa. These have been observed, 3 of them. If the neutrinos are Majorana, which we don't know yet what it is, there are experiments, even in Spain, in Canfranc, you are looking for the double beta decay, which it's a way to say whether the neutrino is Majorana or Dirac. Then the lepton number will be violated, and there will be no conserved numbers. Why the standard model violates, you don't have to worry about this. That's a measure. These are masses of quarks. That's a measure of CP violation. And Rubakov and Kuzmin, Saposnikov, and Gavela, Hernandez, Orlov, and Penne have computed this number in the standard model and found it to be 20 orders of magnitude smaller, 10 orders of magnitude smaller than the observed one. Using some techniques, for instance, they use Svalevans are unstable configurations of the Higgs field. Now we've discovered the Higgs field, so they freeze out the temperature in the universe where the interactions between Svalevans are compensated by the expansion of the universe. The temperature is between this range, but if the mass of the Higgs is somewhere in between, that's more or less, we know definitely now that the Svalevand would predict this temperature, and in this temperature there is this 10 orders of magnitude, so this model cannot explain that. So you have to go beyond the standard model to explain CP violation. Beyond the standard model, of course, so the quark sector with the heavy bodies here, the elephants, the quark sector do not satisfy this. You have to go to the lepton sector to see whether the CP violation in neutrino sector can give rise to the observed CP violation. At the moment, that's we don't know yet because we haven't observed any lepton sector at the moment. of CP violation in the lepton sector. So we have to go to new sources of CP violation beyond the standard one in order to explain things. However, so people, if you assume CPT invariance and Lorentz violation, and several ideas that can provide you with extra sources of CP violation are supersymmetry, extra-dimensional models, massive neutrinos. Even right-handed supermassive neutrinos may provide seamless extension of the standard model, like the Saposnikov model, the minimal new MSSM, new from neutrino minimal standard model, not supersymmetric. These can provide extra sources for CP violation, which can explain the Baryon asymmetry. But you need 10 orders of magnitude. One of the ways, if you use supermassive neutrinos, which we shall use later on in the article, is that you have two neutrinos, Majorana, for instance, that they decay to particles of the standard model and antiparticles, phi's are the Higgses. Here I include also the charged Higgses because you may be high in the temperature, so this not decoupled. They are not Goldstone bosons. They are there. In the low, if the temperature is much lower than these two decouples, then you have only the standard Higgs. But if these rates are not equal due to some reason, then you have CP violation. And CP violation has been observed in loops in several models suggested originally by Fukushita and Yanagida on leptogenesis. So you see there's the Higgs, that's the loop. So it's one loop process if you assume CPT and Lorentz symmetry. There are no at tree level CP violating phases, so at tree level, this process doesn't give any CP violation in the sense of this asymmetric decay widths. But that's the question. Why do we have to assume CPT violation? We will see. I will argue that through a particular cosmological model, quite naturally, you may have a spontaneous violation of Lorentz symmetry, which is, then you may wonder what is the Goldstone boson. I will say something about that. Lorentz symmetry is a global symmetry. But, so which means that it's the spontaneous violation, as I will argue, is like having electromagnetism, which is gauge invariant and Lorentz invariance, but in a frame where you have a constant electric field or a constant magnetic field. The constant electric field breaks rotational symmetry, therefore breaks Lorentz invariance, but spontaneously, quite innocuously. It's just the background that you're considering. Cosmology is you broke the diffeomorphism invariance in any case of the universe because of the particular solution of the Einstein's equation, all right? It's just a particular frame. If you have, in addition, through the condensates that I will argue, of anomalies, a specific frame where these condensates are constant, then you get spontaneously a preferred frame that breaks Lorentz symmetry, and then it will break also CPT, and then it will generate at tree level. You see, this is supposed to be my artistic thing of CPT violation. You have CP violation, but no violation of time, because if you notice, the clock here goes 12, 11, 10, 9, 8, 7. Not 12, 1, 2, 3, 5. So that both clocks are okay. This means that you have time reversal invariance. I'm not genius in painting, so I couldn't figure any other way to show it. That's time reversal conservation and CP violation, so CPT is violated. And then if CPT is violated, you have 311. Now, what is CPT? Quite quickly, you have the quantum field theory is a theorem. If you have local interactions, Lorentz invariant interactions, and unitarity, in other words, probability is conserved, you don't have imaginary parts, then in a flat space-time, the Lagrangian is invariant under the combined transformations in any ordering of charge conjugation, which means that the quantum numbers change flip sign, but not the magnitude. Left-handedness is violated, so parity, and time reversal. And of course, if C, P, and T are conserved, then you may have trivially a CPT invariance, but even if individually all these are violated, the symmetries, you may still have CPT invariance because the amount of violation is or conservation are equal. So you may either violate CP, but the same amount you conserve, it compensated by the violation of T, or conserve it, and everything is fine. If, however, Lorentz invariance is violated, then you may have CPT violation. If you have CPT violation for some reason, you necessarily violate Lorentz invariance through a theorem by Greenberg, who added to this original CPT invariant theorem. But if you don't, you might even have CPT violation, as we shall discuss. CPT violation comes in two ways. Either the CPT operator is not invariant, is not well defined. For instance, you may have decoherence in quantum gravity through quantum degrees of freedom that are inaccessible in the low energy limit. Then we'll prove out that there is a fundamental irreversibility in this case. Or simply there is an innocuous, what I said before, in spontaneously broken, and simply the CPT operator is a well-defined quantum operator, generator of these symmetries, but it does not commute with the Hamiltonian of the system, like in quantum mechanics. And that is the thing I'm going to discuss today, which can lead to matter-antimatter asymmetry. And also the first one, this process leads, but that's full quantum gravity issue. So let me go through this Lorentz invariance violating scenario and how you generate it and what is the role of primordial gravitational waves. No need to explain this diagram. I will concentrate on the very early era, immediately after the Big Bang. I will try to discuss the origins of primordial gravitational waves. The first thing is, first of all, because I will need them, at the Big Bang, you need an ultraviolet complete theory of quantum gravity. It could be strings. It could be other things. We don't know what full quantum gravity is, but whatever from the purposes of this talk, I need them to include a few ingredients. Primordial black holes, who arise not from matter collapse, because there's no matter in the early days, but from quantum fluctuations of the vacuum, and domain walls, which could be biased, and I say what this means. So generation of gravitational waves can be in two ways. If you have primordial black holes by the merging of rotating primordial black holes, you have to be rotating. Or biased domain wall. What does it mean, bias? For instance, you may have, my favorite example is dynamically broken supergravity, for instance, or or supersymmetry. You have a double well potential. This is the potential of the condensate, let's say of gravitinos here. And there is a bias which is generated, for instance, by vacuum percolation effects. You have bubbles of the vacuum, the bubbles of positive and negative vacua, all right, plus and minus. These are bubbles in the universe, here and here, and they percolate, and there is an asymmetric occupation of quantum states in each vacuum, and that creates a bias. It's equivalent to the potential lifting one of the symmetry. If you lift it, you may have a first hilltop inflation here and then a second inflation there, and that's the model I'm going to discuss, because the first inflation, as I will discuss, this is the model that I developed with Jean Charles. I will say a few words next. You have a first inflation quickly, which is not phenomenologically observable. It prepares the ground for having isotropy and homogeneity of the universe, and then it enters the inflation that you observe in nature, which is due to this running vacuum anomaly. And there may be an axion dominance era here in this string version. So the second way of generating gravitational waves is from the asymmetric collapse, from the fluctuations actually of these biased domain walls. You may also have gauge-Zeno condensate, but I'm not going to discuss it. So assuming that you generate sufficient number of gravitational waves, you need to ask the question whether they can condense. That's a difficult question. It depends on the conditions that you have, but let's assume that they do. If they condense, what they will do? They will provide condensates because of this condensation of gravitational waves of gravitational anomalies, which lead then to spontaneous Lorentz violation. The axions will play a very crucial role, and they will induce the Lorentz violation, and through which will be realized through actions, specific background of actions, will lead to inflation and then matter-antimatter asymmetry. That's the paradigm shift I will discuss. Let me very briefly say what is the theory, string theory, and we shall assume that in string theory, the early universe consisted only with external lines of the fields from the massless multiplet, because strings have massless multiplet superstrings, because tachyons are ignored. Of course, if you have tachyons, is a different issue, but tachyons will not affect my scenario, but they will induce additional instability. So at the moment I'm discussing superstrings, no tachyons. You have a scalar field, spin 0, spin 2, which is traceless tensor, which is the graviton, and a spin 1, and the symmetric rank tensor, which is like a gauge field, but with two indices. That field corresponds to a long range force, is a U1 gauge symmetry, and that's the axion. This is the field strength of the axion. This is like if that had one index, it would be F mu, F mu. Now, these gentlemen come in and say that in string theory, unfortunately, you have anomalies that you need to cancel in the extra dimensional, although we will leave some of them in the 4 dimensions. And in order to cancel them, you need simply, this would be too technical for a colloquium, you have to add these so-called Chern-Simons terms. You have to modify, just skip this issue. You have to modify the field strength of this. In addition, from this, you add these terms. This is a spin connection, and this is the gauge field. If you take this identity, the external gravitational derivative on this, and the epsilon, therefore the external derivative of that, then you get this identity. So it's a constrained quantum field theory if you have this modification with this, the constraint. That is how the axion will be implemented in this field. So you have this axion with this modified curvature. Notice here something interesting, that you can absorb this into a generalized curvature, which is no longer symmetric, because this is totally antisymmetric, and that's torsion. And that is a field that can persist only up to order alpha prime, but that does the job. And now, let me see how you get action from this theory, from the age, actually. The actions can be classically observed that in 3 + 1 dimensions, this relation determines uniquely the degrees of freedom that you have. You have a totally antisymmetric tensor, you multiply it with this Levi-Civita tensor, and you get this. That's the derivative, that's a spin 1 because of the theta, but that's a spin 0 and pseudoscalar. And that's the field classically. This classical field, of course, comes from this gauge invariant, and therefore this is a pseudoscalar that corresponds to a long-range force. This is a new long-range force that string theory has. Formally, you can implement this constraint, as I said, in this path integral, integrate over age, and because the age is quadratic to this order, you get this, you get the path integral, the multiplier field, which is the B field, this dual field, becomes dynamical, and you get immediately the anomaly. I didn't discuss gauge field here, that's why I cancel it, but in general, you get all the gauge fields as well. And in string theory, this coefficient has a particular value, which is the ratio of the 4-dimensional Planck length with the string scale. This doesn't necessarily mean to be equal to the Planck length. String scale is a free parameter. So that's how you got the anomaly. You got dynamically the anomaly of the axion by implementing it through a constraint. It has to be pseudoscalar. Why? Because this, if you implement this constraint as a delta function in the path integral, I'm saying that only for the people who know, that's that's parity violating. You don't want to introduce any parity violating thing in the action, and therefore you get this parity conserving term, and B has to be necessarily pseudoscalar because this term violates C and P, violates P and CP. If you have this term, then you observe that unlike the gauge term, which is topological and does not contribute to the variation of this with respect to the metric, these depend and contributes to the so-called cotton tensor. This is the problem. The fact that this contributes negative contributions to vacuum energy is not a problem. What is the problem is this. If you write Einstein's equation from this axiom with respect to the variation of the anomaly, you get this. And you see, observe, this term you can find because of its definition that you get from varying, that satisfies this equation. This is the derivative of the action. And of course, if the action is constant, this term is total derivative, so it doesn't contribute. If it is not a constant, then you think that the matter is not conserved because of this term, because of the anomaly, and therefore that's what you would say it spoils diffeomorphism invariance. But that's not true because you always defined an improved tensor by bringing it trivially on the left-hand side. And what is this improved tensor shows is it tells you the exchange of energy between the gravitational action, because this is a field in the gravitational multiplet of the string, with gravity. And therefore, there's no problem with on this particular setting with the diffeomorphism invariance. Now, let me go to the spontaneous violation of Lorentz symmetry and then move to the final topic on the matter-antimatter asymmetry and inflation. The spontaneous violation of Lorentz symmetry, I don't have the time to go through details. I may, for those interested, tomorrow I was given the opportunity to explain some of the details. All it means is that I will consider the gravity wave as a condensate. In other words, they will lead to this being approximately constant to this quantity. I will estimate it within weak quantum gravity, but I need chiral gravitational waves. In other words, left and right asymmetric. So I will consider a background of the expanding universe, Friedmann, Lemaitre, Robertson, Walker. I will put it by hand, but then I will consider chiral fluctuations above this. And this is the scale factor. I will consider graviton modes canonical quantization. I will graviton modes up to a given cutoff because it's an effective theory. And in string theory, this it's a long discussion why this is so, but this could be identified with a string scale. Once you do this, that's what you find. And this I will consider, and this is the condensate because this is the microscopic occupation of the ground state. And there's a number of sources of gravitational waves that you may have, either domain walls collapsing or black holes. That's the number, the total numbers, the density if you have, a local situation. So what I will argue is that the time derivative of this field is proportional to age, and therefore this is constant during inflation, and this breaks Lorentz violation. So once you enter in an inflationary state, this becomes constant and breaks Lorentz symmetry. Why? Because remember this duality relation. When the sigma is 0, that's the b dot, the time derivative of b, and ijk, the rest, this is totally antisymmetric. So if mu is 0, all the other indices have to be spatial. And this is like, remember, age is like the field strength of a gauge field with two indices. It's like what I was saying earlier. It's like an electric field or a magnetic field having a spatial direction fixed, constant being along a spatial direction. So that's spontaneous breaking of Lorentz symmetry at each time, at each moment, because you have the scale factor. So in flat space-time or at each time slice, you have the edge violation, rotation is broken. Now you may ask, what is the corresponding Goldstone boson? Well, the axion itself is massless, and that's the only field you have, apart from the graviton, which cannot be the Goldstone boson of the symmetry. But because B breaks the symmetry, that's what I say. Perhaps this is the Goldstone boson of the spontaneous breaking of Lorentz symmetry, which is a global symmetry. Of course, in supergravity, Lorentz symmetry becomes local. So that's what I say. Perhaps you may not even need the Goldstone boson here. That's another question. So once you have this constant, what you do with the condensate, you observe that the condensate becomes h to the fourth. And that's the important point. That tells you inflation without external influence of the running vacuum model. I will explain. First of all, undergraduate physics. If you have the scalar equation of motion in this curved background, if this is constant, then if this is slow and this is constant, self-consistently, you get again the self-consistency that the age is constant, and therefore you have inflation. So if you have a constant, for some reason, dB over dt implies constant age, only if this is constant. So this is a self-consistent argument that things are okay, but I need a microscopic understanding. And the microscopic understanding starts from this action. If this is constant, then you have a linear action. That's the action part of the action. You have a linear action, potential, but unbounded from below. In this particular thing, in our convention, this is negative. In string theory, for those who knows, in brane theories, you get linear action potentials from the so-called monodromy, but through some special convectification, which implies that the brane in 4 dimensions are square roots of b square. For large b square compared to this scale, which is a quantity of the scales of the string, you get this, and you're up to here. That would be like a minimum of the potential. This has no minimum here, so you have to contrast it. Even if you don't have minimum, the dynamical system analysis indicates that there is a metastable inflation. And that's where there is a problem. You would say, how can I have a a running pseudoscalar thing and have inflation? And that's where the running vacuum model comes to the rescue, because this is not really a constant. It depends on h to the fourth, as I tell you. Okay, it depends on h to the fourth. H varies slightly with the time. It is never constant, even in inflation. And that means there is a nonlinear gravity. So what you think as a constant is like a drift velocity in Brownian motion, right? It's because of the nonlinearities of the system. And the inflation is due to these nonlinearities. And the exit from inflationary heating comes because of the decay of the vacuum itself. So you don't need fundamental inflatons here. This triggers inflation, but it's not the field that leads you to reheating. So the inflation and exit is a consequence of nonlinearities in gravity, according to the running vacuum. Moreover, this BI-BF, initial and final condition, the inflation last here is a metastable system, and this is of the same order. And that more or less means it's like de Sitter. This is approximately constant. The condensate times B is approximately the same order of magnitude, and it looks like a de Sitter spacetime. That's how you get inflation. So very quickly, here are the dynamical systems. These are variables pertaining to the derivative of the potential and of the dot of the running. And you see the inflation is here. It's a metastable system. These are flows in the phase portrait of the linear potential. There is an era preceding inflation, which is a stiff era, where only the axion, this is 0 in the stiff era. You don't have condensation or gravitational waves, so it's only a massless axion without potential. The equation of state is 1. That's one shift, and this is inflation. And then again, you go from shift. So you have this sort of, if in a diagram between the Hubble potential versus the scale factor, you are here, and then you enter inflation. And inflation is a saddle point. It lasts only for a few foldings and goes away. It's equivalent to this. All right. But what inflation? The RVM inflation. This is RVM inflation, but you get the equation of state to be -1, almost. That's exactly what's happening. And you see that the B dot, this happens because of specific initial conditions. That's what the dynamical system is. You choose specific initial conditions. Now, don't ask me why you chose those. You chose those because these initial conditions, as you know very well, the problem of initial conditions of inflation is a very complicated one. And inflation is supposed to be improbable to happen, all right? Because of this, in the set of initial conditions, this is what happened. But these initial conditions can be chosen, and you get this order, you see, with this initial condition, which are here. The inflation these are various initial conditions, and the one that leads to inflation is this, okay? Here, these two, the black, 006. If you choose this, then you get these numbers. And if you get these numbers, the resulting vacuum energy is that's exactly what is called a running vacuum. The energy density, the pressure are even functions of the Hubble parameter. Simply that's what it means. And the equation of state is more or less -1. That's a running vacuum because it's not quite constant h. This is a function of h squared h to the 4th. In fact, this form holds even h to the 6th if you include quantum field theory in modern era's corrections. And it holds continuously from the inflation to where the coefficients may change, of course. It may not be quite continuous. And inflation happens because of the nonlinearities of this term, which is dominant in the early universe. And that, if you write down, I don't have the time to explain, if you write down the flow of the Hubble parameter in this framework, in the running vacuum framework, you find that an early era corresponds to a constant h, which is the inflation. There is the estimate of this can be done. You can estimate it by looking at the detailed passage from the stiff to the RVM era, by matching conditions of the stiff condensate, which you can compute, to and again, they are both h to the 4th, but they have the different coefficients. And essentially, this is why you need the sources, because the NS, the number of sources, each one of these condensates depends on a number of sources. And suddenly you need to have a condensation, which occurs if you have appropriate conditions. Therefore, large number of sources, suddenly they have to enter and condense and give you the inflation. And the inflation is metastable because the condensate have imaginary parts if you compute it, and that saves you from Swampland if in string theory, because string theory tells you that this eternal de Sitter space does not exist, is not consistent with quantum gravity. But if you are metastable, this is fine. And this is the number of the imaginary parts, never mind the formula. If you compute the imaginary part of the condensate and you match it with the inverse, this is the Hamiltonian of the gravitational waves, that's the lifetime, And if you want that to be 50 or 60 folding, which is the Planck phenomenological result, consistent with what we believe today, or less than that, a bit bigger than that, then you get a constraint on the string scale here. So the string scale is a bit less than 0.215. That's important for this. Now I'm going to the final talk in the next 5 minutes. Is that okay? Okay, very good. Very good. So why this? I told you that before, the equation of motion of B and the condensate gives you, this is the time derivative of the current. Remember that Chern-Simons is the total derivative. That's the argument of the derivative. And then this is the time dependence in the isotropic and homogeneous background. And this B dot is constant. If B dot is constant and has this value, which the dynamical systems have determined, then this is important for leptogenesis. Why? First of all, at the end of inflation, there's something that we don't need. Up to this point, we had gravitational waves, right? Which I told you are due to this action. The action is a gravitational field, and that's okay. It's part of the gravitational multiplets, is allowed to interact with gravity because it's part of is the spin one part of the multiplet. I don't want to have gravitational waves of ordinary matter. I don't want to have anomalies in ordinary matter. Although it would be all right, it might change completely the cosmology. So in our paper, we impose that the anomaly cancellation will not happen in the beginning as happened in Green and Schwarz, but at the end, because at the end, the RVM inflation will decay. Until now, I had only bosonic degrees of freedom, axions and gravitons, the dilaton, I fixed it. And then at the end, you will have chiral matter, fermions. The fermions have anomalies, and this chiral matter generation due to the decay of RVM inflation will cancel the gravitational anomalies, the primordial ones that I have through the string case. So this cancellation from radiation onward, I will not have Chern-Simons gravity. So in this model, don't look for parity violation in late eras. You have to look for parity violation due to the gravitational, in the profiles of the gravitational waves that are produced during inflation. Then you can find out that the temperature dependence as the scale factor is 1/T. That's a cosmic temperature. Is like this. You may have chiral anomalies generated because the cancellation of anomalies concerns chiral anomalies are still allowed. The Chern-Simons cancels the gravitational anomalies, but not the gauge part, not the F mu part. So that's more or less the temperature dependence as the universe cools down. This is sufficiently low, slowly varying during the leptogenesis epoch to consider this constant. And that is, if you have a constant, almost constant B dot, that is a model of leptogenesis that requires only a minimal extension of the standard model with right-handed neutrinos, and you get it. And you will see, you get also baryogenesis. So if you have right-handed neutrinos in the early universe, as in a model that Sabin Sakharov and my ex-master student, Cesare, and my PhD student, Tom Bossingham, we have studied. If you have right-handed neutrinos, that's their mass. They are Majorana neutrinos, so that's conjugate, that's the Majorana mass term. But if you have a background of this form, constant background, B slash, gamma 5, plus the standard portal that connects the lepton, this is the lepton doublet, neutrino, ordinary neutrino over electron times the Higgs doublet, times the right-handed neutrino. These are standard terms for leptogenesis, but not this. This is, in my case, this is nothing but the background. If you have fermions, remember what I told you, that the H mu nu rho, that I didn't want to deliberately, I don't want to show you the formula, but I can tell you in words. The H mu nu rho, this field strength was a torsion. A torsion appears in the covariant derivative, the gravitational covariant derivative. Torsion means this sort of strange, the asymmetric stress, the asymmetric Christoffel symbol. And you can show that a torsion, that's if B mu is this B dot, that's how it would appear. This is a theory with torsion, constant torsion, or torsion of that form. If it is or constant, the B dot, or approximately constant as we have seen, then you know from the standard model extension of Kosteletsky that that's nothing but a standard Lorentz and CPT violation term, because you can prove that both these the term is not invariant under the action of both the charge, the P and T, and the Lorentz, and violates Lorentz because it's B dot, because it's constant. But it's spontaneous violation. They are verbs. That's how it comes. The magic comes because then you, because of this background, which you don't have in standard model, you see that the rate, the decay rates of the right-handed neutrino are different because of this B0. Omega is B0 m squared. So you see that if B0 is 0, these things are exactly 0. And that's the old part in the CP violating phases, that at 3 level you didn't have. But here is not a phase. This is just a 3 level. This is due to the background, interaction with the background. So the only thing that you need is to tune the background and not the phase, which is easier. So contrast with the standard CPT conserving case. You need loops to get both diagrams to get this asymmetry between standard model particles and antiparticles, but not in our case because the background introduces this CPT violation. CP is violated necessarily, and then this. So that's the thing. Then you can compute. You see that to reproduce, as I tell you, you need, unfortunately, we don't know exact microscopic string theory so as to compute the condensate. The condensate would tell you what the number is, the B dot, but we only did the estimate with quantum gravity. So it's not, you don't know what the massive states. But if you accept these numbers, then you see that this number is 10 to the minus 8. You need that to get this Lambda number over the density of the universe, and with some numbers of the portal that you borrow from particle physics, that's still phenomenology, but this is consistent with light neutrino masses and stability of the Higgs vacuum at one loop, because you don't want to destabilize that. You observe that even if B0 is not constant but varies in the immediate exit from inflation due to the cancellation of gravitational anomalies by the chiral fermions before generation of chiral anomalies, varies like the cube of the temperature. This is practically constant, and these numbers persist. These leptogenesis can be embedded, of course, in other existing scenarios. And then, if you produce the leptogenesis in the right order, you can use Svalevon interactions, which violates both baryon and lepton number, but preserve B minus L, as I said. And therefore, if the L is violated by 10 to the minus 2, the baryon number is also the same because this is conserved. And that's how you get the leptogenesis. That's the standard processes of, Higgs times square thing. That's the equilibrated B plus L violating Svalevon interaction. Never mind. Another amusing thing is that because this M at the moment was put by hand, but it can be generated by torsion, by condensates. And if you have a condensate, then you don't have to compute anything. For instance, you need, instinctively, you have more than the gravitational action. You may have a compactification action. And this compactification action may couples to this right-handed neutrinos, like this, with some Yukawa couplings by hand. But then the B couples only to the torsion, to this anomalies, not the A. Although you can also couple to the A in more complicated models. These are gravitons. These are chirality changing, chirality preserving vertices. And this is this kinetic mixing. This model is like in dark photons, you have a kinetic mixing between the U1 photon and the dark photon. Here you have between the scalars, the axions. And once you have this kinetic mixing, you generate in the propagator of the right-handed neutrino, you generate a radiatively induced mass due to torsion, and you can show that it has this form. Never mind if you have 3 vectors, 3 neutrinos, like 3 light neutrinos and a symmetric 3 right-handed neutrinos, which is a symmetric model, then magically you observe that this mass is independent of the cutoff, of the ultraviolet cutoff. So that's an observation. Finally, I'm not going to say anything about dark matter. Simply the axion field acquires a mass through chiral anomalies. I show you this, and that means that the axion mass in this particular case can play the role of QCD action, but it depends on the scale of this potential, which doesn't have to be the QCD scale. Now, so if it is like this, then the action is associated with torsion, and if the action acquires a mass and plays the role of dark matter, then you have a geometric origin of dark matter, because torsion is geometry. And now is the final, my final 2 minutes. I'm discussing the later occurrence, which will tell you what phenomenology this model might have. And of course, apart from the obvious deviation from lambda CBM, is the alleviation of the tensions. what did we do so far? So as to understand, we started from Big Bang, pre-inflationary phase. We got to the Sitter phase. We had the gravitational anomaly, which leads to these actions. The gravitational anomaly during inflation leads to a constant B dot, the rate of change of this action, which remain constant until the exit, where the anomalies have been cancelled. But after the exit, because it was constant until the very end, it starts dropping with a temperature like this. So that's the prediction of the constancy. That's slow dropping. This leads to the leptogenesis. And now in the matter era, this may acquire a mass. And in the modern era, we are going to discuss it now. And we will see that the phenomenology tells you that if you parameterize this action in the early era like this, with a 10 to the minus 2, more or less is the same order. We'll see that. That needs understanding microscopic, but let's see it. So this potential, this background, torsion background drops like a temperature today. Today, the chiral anomalies dominate after a given time. And if they dominate until today, that's the value that you get if you match this value, because the temperature at inflation is the Hawking-Gibbons temperature, which is essentially H, the Hubble of inflation. And if you match it with today, you get that smooth running. This running is consistent. This is a Lorentz and CPT violating term in the standard model when it comes to fermions, and therefore these are the limits. It has to be less than 10 to the minus 2 eV or 10 to the minus 22 eV if the spatial part. The spatial part you have to worry about, because you could say, oh, but that's B0, so I'm fine. No, you are fine only in the cosmic frame, but our frame today on Earth has a velocity compared to the cosmic frame, which has been measured to be this. Despite being small, you have this factor. You generate a BI with this factor, and then still with that, you can see that this is very consistent. Another important point is that today the H0 is 10 to the minus 33 eV. So you see, today, this number that you get from today implies that the epsilon is of order 10 to the minus 2, right? So, of course, this is the number that gave you the leptogenesis, B0. So it might be something that we need to understand there, why the number early enough and the number today is more or less the same. From Andrea Gomez-Valent, who is here, and Joan Sola, who is here, they studied the running vacuum today, where it's only the H square term. Remember, the H vacuum has H square, H to the fourth. The H fourth doesn't play any role, but the H square plays a role today. This is the constant today, which we don't know its origin, and might be just a subtraction point in quantum field theory. If you do this, you find a running time today, but we need to understand microscopically the era. The stringy, our model that I was discussing, also leads to logarithmic corrections, and the same also quantum field theory. Now, these logarithmic corrections is a long story, but you not only have this, but for instance, if you are in a de Sitter space and you do the analysis, you find that when you integrate out one loop gravitons, you also get in the effective theory this sort of corrections, and that's age in the background. So the vacuum energy density will have this form. Surprisingly, Big Bang nucleosynthesis should be consistent if the dn has this range, and that is actually the range that you find also in the 10 to the minus 3. It's quite consistent with this. Now, and another amusement is that if you do, suppose that you start to remember, I mentioned dynamical supergravity in the beginning. If you assume a smooth connection up to today from this model, then you find the similar logarithmic corrections in the early supergravity model due to dynamical symmetry breaking with these numbers. And kappa is Planck, inverse Planck square, and F is the scale of the supergravity, the gravitino, essentially the gravitino condensate that I mentioned before. This means that with these numbers, you can alleviate these tensions. So that's, to me, is surprising. I mean, pleasantly surprising. So with this number, you fix the parameters to satisfy this scale, which is the scale of supergravity, and this is almost of order Planck. So if kf square is of order 1, that's what I mean. Then you see that Our model is sensitive more to sigma 12 rather than sigma 8 tension, which is the growth of galaxy. What is sigma 12? If you notice, sigma 8 tension is the mass function in spheres of radius 8, h minus 1, h small minus 1 is the reduced Planck Hubble Planck S. And as pointed out by Sanchez, a better quantity is probably the sigma 12, which is defined as mass radius in 12 and Planck without necessarily implying a knowledge of age. If age is 0.67 or about, then of course the sigma 8 is sigma 12. Of course, with the string tension here, you better, I mean, there is some uncertainty here, and Sanchez has been suggesting that this might be a better number, which is what we used in our paper with Adrian, and what, as you will see, Joanne and Adria used it also to model the X CDM of the phantom matter. So this model fits the tensions. As I said, logarithmic terms also characterize, but they have a different origin, quantum field theories. They arise from integrating out quantum fields, ordinary quantum fields, not supergravity scale of the sitter or gravitons. Our logs appear from due to integration of gravitons. And finally, this is the fit on our model with the sigma 12, and you see that's the lambda CDM, and that alleviates the tension quite consistently with the numbers. I compare it with other fields that De Cruz Perez and Moreno Pulido and Joan and Adria Gomez Valent have done. This is the type 2 RVM, where the best fit is if you allow for a mildly varying Newton's constant. The logarithm that I said there corresponds essentially to that, right? Because sigma 1 plus logarithm is equivalent to having, I mean, if you have a model like this, it's like having a Newton's constant which varies, because that's the coefficient of the Newton's constant, which varies with time mildly. So that's like the type R RVM, but here is gotten from first principles. And the phantom matter. What is phantom matter? I mean, this model contains a phase in which the equation of state is like that of RVM, rho equals minus P along the diagonal, but the energy density is negative while the pressure is positive. In the standard RVM, the energy density is positive, but the pressure is negative and you have expansion. And then you will see that there in this model, you get the best fit if you do all this full triangle, much better than other models. Actually, and it's clearly there is the tension of the lambda CDM. This model is comparable, as I said, to our fit if you take from the supergravity, but of course we have more freedom if that's not the case. So that more or less closed what I wanted to say. That's the model that we use. So it's a modified gravity, but with anomalies. That is like an FFR gravity in a specific form. That anomaly, they play a role in both inducing inflation and leptogenesis, and that's why it's a Chern-Simons gravity. This is what I discussed before. Here is you have the gravitational wave condensate formed at the end of the stiff era, where you have a sudden increase of sources, of gravitational wave sources, and this is the graceful exit. Inflation is the saddle point, so you have to have an exit. Both inflations, this model has two inflations, as I said. Both inflations are characterized by imaginary part, but of different origin. It involves spontaneous Lorentz violation and anomalies. And I try to argue that we exist because of gravitational anomalies. Now, if I have, do I have 1 minute to say the condensed matter, or I can? It's only 1 minute. What I mentioned before is this. Now, what is this experiment? There are works by Lance Steiner and who is in Madrid, by the way, and he used to be at it. I think he is. And Luttinger in 1964 associated thermal transfer phenomena in metals with gravity, classical gravity. But in the presence of chiral fermions in a material, you have gravitational anomalies. We know that. That's the gravitational anomaly. So that's the standard field, and that's something that you think that in a flat space-time you may not have. However, because of this term are associated, BA is 2 for each pair of chiral fermions if you have in the semi-metal. You know, semi-metals are, what are the semi-metals? You have nodes in the Fermi surface. You expand about the Fermi surface and you have a relativistic dispersion relation in terms of the speed of sound. And that's like relativistic fermions. And there, the energy, considering the Kubo approach, the energy current for the Weyl fermions consists of two terms. In terms of the magnetic field, a term that depends on the temperature, where the Ag is related to the B, to the anomaly. All right, X is whatever it is. So for semi-metal, if it is 2, it's 112. And this is a standard thing which is not related to gravitational anomaly. So the claim is that if you have a temperature gradient and you have a magnetic field proportional to the temperature gradient, you can generate, if you have an anomaly, you can generate this energy current, and this energy current then affects the particle density and the conservation equations. And you measure it experimentally. They measure experimentally this. They arrange in conditions so as not to have this, because they consider only a temperature gradient, so they only have that term, not this term. They have a zero electric field, so this term didn't exist in the energy density in the change. And they observe this, so they say, I trace back this if we assume this. Of course, to me, you don't know. You may have other microscopic mechanisms that generate the Ag, which I don't know. But if you don't, then precisely that's their argument, that even in a flat space-time, due to quantum effects and transfer phenomena, chiral anomalies might play a role in semi-metals. And they published this result in Landsteiner was one of the authors in Nature. So that's it. If you believe that we exist through anomalies, I don't know, is the answer. I try to convince you of this. Thank you very much.
Okay, thank you very much, Nick, for this nice talk and this overview of the situation about anomalies. So now there is some time if you want to ask a question. I will bring you the microphone. Do you have any question? Okay.
Yes, thank you. Okay, so I wanted to ask that normally I understand in ordinary inflation, you have this inflaton or some field, and then there is this period at the end of reheating where the energy in this field becomes the radiation and everything that is in the next phase of the universe, for the Friedman phase, right? Expanding phase. But in your case, you say there is no inflaton, you have this alternative. So then what I didn't understand, I think you explained some of it, but I probably didn't understand it well.
How the reheating?
How does this reheating take place, and where does the energy come from, right? What is it that generates all the radiation and stuff?
Yeah, very good. So, in fact, I have it. I didn't speak to, but thank you for asking this. And this is okay. What I said is that, first of all, that was the first of my spares, which, if someone was asking this, that's the running vacuum. That's the flow equation, because rho dot, because H depends on dot, rho dot satisfies this, and that's one of the solutions, which is inflation. Now, these nonlinear terms lead inflation, but what do? They also, if you plot at the end of inflation, if you put the temperature, the vacuum has energy, because of this H to the fourth term. So that's the vacuum energy. And the vacuum starts decaying. The H starts decaying. And so the energy comes because, remember, the condensate that leads to H to the fourth carries energy with it. It's not zero, the energy. And that has to relax. So that is where you see the reheating. The reheating comes because of immediately, because A in the beginning increases with temperature. At the end of inflation does that, and then you pass through the standard radiation, which is A to the fourth. So the reheating comes from the H to the fourth terms, comes from the running vacuum itself, not from oscillatory details of the axion, which they don't do. It's just you get the inflation from the linear potential of the axion, in the sense that I talked about, but because of the energy of the condensate.
It comes from gravity itself.
It's the quantum gravity itself. It's the vacuum of quantum gravity, of quantum fluctuations. That's the non-linearity of gravity. And that's why it doesn't conserve if you have the anomalies, relative, they don't conserve the ordinary matter, d mu, t mu, nu is not zero because of the anomalies. There's an exchange of energy from the vacuum. So the vacuum is not really, the anomaly makes the energy density higher than the vacuum. So it's like, it's not an excitation because that is the vacuum, but is a false vacuum. You see, it's a false vacuum, which means that its energy lies higher than the true vacuum, which is when the anomaly is not there, and that's how it's like Higgs. All right.
Yeah.
If that answers, I don't know if this answered your. I mean, partly, but of course, technically.
If you allow me to clarify, this is not a Stravinsky. Okay?
Yeah.
Because in the case of the Stravinsky, we don't have inflation through H equal constant. Okay, in Stravinsky, actually what we have is H dot constant, not H equal constant.
That's right.
So in this sense, this is a mechanism which is completely different from Stravinsky. That's why it is called RVM, running vacuum model inflation. Any other question?
So there is something I didn't quite understand. So the H naught tension, do you relax it through an early time modification or through a late time modification?
Through a late time.
Okay.
It depends what you. Okay.
Well, CMB or so before a combination or after a combination?
After.
So
because of the running, because of the.
Yeah, but if you do after, then
I can say one more. Yeah, let me show you the number. Yeah, I need this model. So this model, I mean, to answer more precisely, I can only apply it when the situation is approximately de Sitter to have this form. So the question is, when is approximately de Sitter? It's not at the if it's not the CMB is not de Sitter, right? Is not the cosmological constant is not quite constant, so as to be approximated to a good approximation. I have a freedom, but in the paper with Adrian, and Adrian is here, we use the current after the CMB.
Right, but then you have H of Z measurements and dA measurements that they put very tight observational constraints in such a way that I don't know how it's possible that you make the model to go to the H naught that the supernova wants at redshift 0, but just passing through the H of Z measurements that, for instance, VO tells you that they have to be. So it's not clear how you're, or essentially, if you could show the plot of DH, the dA of Z and H of Z of this model and lambda CDML, that would be more clear how you essentially relax this.
Adrian can answer here as he used the phenomenology.
Yes, actually, in this model, there are two parameters. The one that controls the effective gravitational coupling at cosmological scales, and the one that controls the running of the vacuum.
And we have also the running of the running.
So here, what is making the job, apart from the running that allows you to have perturbations at nonlinear scales under control, is the amplitude of the Newtonian coupling, which also plays a role at the recombination epoch. So it's not only a late time effect; it's a combination of late time effect and something that is going on at the decoupling era. Yes, that's true. Yeah, but notice. Imagine that you change that you shift the value of G both at late times and at early times. Then you can keep the sound horizon. So the ratio of the sound horizon and the angular diameter distance to the last scattering surface constant, respecting the constraint. For instance, the location of the peak of the CMB, of the first peak of the CMB, you can respect that. Yes. So we use the full CMB likelihoods.
I mean,
well, yeah, it might be quite surprising, but it's what we found.
Yeah.
Yeah, but in dark energy, for instance, you also change. You introduce a lot of energy in the last stages before recombination.
So that would be like an early dark energy type of.
Oh, sure. Definitely is an early dark energy. I mean, the running vacuum is. But yeah. Yeah. Oh, yeah, we have to change something. Otherwise, if we go with the lambda CDM, then we wouldn't get any of it.
Well, we use the data on large scale structure where
That's all we have. I mean, the more tests for the model, even if it is falsified, the better. I mean, but the important point is that these terms come from this. If you have KF equals of order 1, you are free to modify this, and C1, C2 are free parameters. So. Plus whatever else we have. So, I mean, the idea is not different than, this is like an f of r, gravity. The log r is an f of r. It's a modified gravity. That's.
But coming from.
But coming from microscopic things.
From a string scenario.
Yeah.
I don't know if there are other questions or comments. If not, okay, so let's thank the speaker again.
Thank you very much.